All right, so today we are going to be talking about dilutions and specifically looking at dilution factors. So, a couple of vocabulary words that we want to go over before this lesson starts is a colony forming unit, or is also known as a CFU. A mole is a unit of measure that is part of the International Standards of Units. It's the amount of stuff in 1 liter, like the amount of weight of one chemical in a liter of solution. And this is 6.02214076 times 10 to the 23 power of atoms in a certain amount of weight. Serial dilutions, say stepwise dilutions, a series of dilutions where the dilution factor stays the same for each step. And then finally, a fold is the factor by which a solution concentration is reduced, often expressed as a multiple. So 1 to 5, 5 to 20, whatever it may be. So why do we need to dilute? Well, let's say a culture contains about 1,000,000 colony forming units. At 1 CFU per second, it would take you 11.6 days to count, assuming that you don't stop, eat, take a shower, sleep, use the restroom, whatever it may be. You are just sitting there counting for 11.6 days. So obviously, we need a better way. So that better, or one of the ways that we can look at is called a viable plate counting method. And it's the only method that can tell a live cell from a dead cell. For example, there are still 500 colonies on a Petri plate, and that would look like that photo. Like that right there is a ridiculous amount of bacteria to count. So what if you're trying to count a population of thousands or millions? It would literally look like a lawn of grass. You're not going to sit there and count every single blade of grass in your front yard. You don't want to sit there and count thousands or millions of bacteria. This is where dilutions come in and save the day. Not just dilutions, but serial dilutions, meaning dilutions over and over and over again to get a desired concentration. So why do we need to dilute? So why do we dilute? Honestly, it's to count less. I don't want to count that many, so you don't want to count that many anyways. But hey, at least we don't have to count millions of bacteria or atoms or whatever it may be. Also, why do we do it repeatedly, like in a serial dilution? Well, every time we dilute, we also plate. And that's because we don't know how much dilution we need to begin with. So every dilution in that serial or that series, we make a new plate to incubate if we're specifically talking about microorganisms. So we might do 5 dilutions and grow 5 plates, and then we end up throwing away 4 of them. It sounds wasteful, but it is much quicker than doing a dilution, plating it, and then finding out that that dilution was not low enough and having to start all over again the next day. You've now wasted a day instead of doing it all in one day. So, of course, lots of things can be diluted, not just blood samples or bacterial samples. We can do something every day. So here's an everyday scenario, and it's cold coffee. So cold pressed coffee is a super concentrated, strong form of coffee that starts out with a zillion molecules of caffeine per cup. In order to actually be able to drink the stuff, you have to dilute it or your heart explodes. For example, how would we dilute? You can put 1 cup of cold press into a pot of coffee and add 9 cups of water, and then we have a dilution. how many molecules are in the original pot of coffee? We have a zillion molecules in that original pot without any water added. How many cups of coffee are in the pot? 10, right? Because we've added 9 cups of water. So what is our dilution there? So if I pour 1 cup from the pot, right, that's mixed together with the cold pressed coffee and the water, how many molecules of caffeine will it have? Well, it would have 1/10 of a zillion, or a zillion over 10. A tenth of a zillion. So, yep, a zillion over 10. So how do we do this? We look at a dilution factor. The dilution factor, it helps to simplify your actions for serial dilutions into dilution factors. And when we say that the diluted coffee was 1/10 strength as strong as the original, we're talking about the dilution factor. We could have also said the dilution factor was 1/10 or 0.1, depending on what the question is asking you or how you would like to do it. So let's look at some simple dilution factor practice. If I have 1 milliliter of coffee and 4 milliliters of water, what is my dilution factor going to be? Yep, 1 in 5, 1/5, or 0.2 would be my dilution factor. If I had 1 milliliter of coffee and 9 milliliters of water, what would my dilution factor be? 1 in 10, or 1/10, or 0.1 would be my dilution factor. Then the last one, if I had 1 milliliter of coffee and 99 milliliters of water, what would my dilution factor be? 1 in 100, 1 over 100, or 0.01 would be my dilution factor. It's not super hard. It is actually easier for you just to remember it is what you're adding to what you want over whatever. But there's an equation for it. So the equation would be, if you want, dilution factor equals the amount transferred divided by the total amount. Or it can be written as dilution factor equals the amount transferred divided by the amount transferred plus the amount of water added. So if we look back at our former examples, it showed us 1 milliliter of coffee plus 9 milliliters of water would be 1 over 10, what I've added to my total. So now that we have gotten through what dilution factor is, let's look into something a little bit more complicated called an overall dilution or total dilution factor. Now, we're super comfortable with dilution factors. What happens if we dilute and then dilute again? For example, we could take that super strong coffee and dilute it by 1 to 5, and then take that 1 to 5 dilution and dilute it again. So it would honestly look, I've got my pot of coffee here. I have a 1 to 5 dilution, and it came from my stock. Right? And I can do it again, and I would now be having a stepwise dilution. Right? So my overall dilution here would be 1 over 50, or 1 zillion over 50. So here are the rules that you need to know for overall dilution factor. To find the overall or total dilution factor, Simply multiply the dilution factors for each step. Let's look at a practice problem together. What is the final dilution factor if we start with a concentrated stock? We then dilute 1 milliliter of stock to 49 milliliters of water, then 1 milliliter of result to 44 milliliters of water, then finally 1 milliliter of result to 9 milliliters of water. So what we would do to start breaking down this process is writing dilution factors for each one of these. 1 over 50, 1 over 5, that's a bad 5, and 1 over 10. And then what we would do is start multiplying these together. So 1 times 1 is 1, and 1 times 1 again is 1. So 1 over 50 times 5 would be 2,500. 2,500 times 10 would be 25,000. So my overall dilution factor would be 1 over 2,500. Super simple. This part of the lesson, we're going to take dilution factors and scale downwards into our serial dilutions. So there's a couple of different ways we can do this, and we're going to look at them. So now that you guys are awesome bosses at finding the dilution factor, let's scale down. If you know the original concentration, you can easily find out the final concentration through this simple equation. Final dilution factor times initial concentration equals final concentration. So let's do two examples here. So I have 7 moles of HCl, and your teacher tells you to perform 7 5-fold dilutions. What is the final concentration of the third dilution? So I want to do this. There's a couple of different ways, but first I'm going to write my equation. So, oops, let me grab a pen. Final dilution factor equals, not equals. Pens are struggling today, times initial concentration equals final concentration. Awesome. So I can tell you my initial concentration already is 7, but let's figure out that final dilution factor. So we want it to the third dilution. So final dilution equals dilution factor 1 dilution times dilution factor 2 times dilution factor 3. So it would be, if we remember from our vocab, a fold is telling you what the dilution factor is, and that is 1 over 5. So 1 over 5 times 1 over 5 times 1 over 5 will equal my final dilution factor. And that equals 1 over 125. Now if I multiply, right, I'm going to plug back into my original equation. 125 times 7 moles equals 0.056 moles would be my final dilution factor. Super simple to figure out. Now, let's look at our second problem. I'm going to erase this down here so I can throw up our next problem. Why isn't it okay. Oh, wow. So now it's asking us to find the final concentration after the 7th dilution. So once again, I'm going to use this equation, but I want to figure out my final dilution factor. And that is going to equal dilution 1 times dilution 2 times dilution 3 times dilution 4 times dilution 5 times dilution 6 times dilution 7. There is an easier way we can do this. We can take our final dilution factor and do our dilution factor to the power of 7. Doesn't always work, especially if there are different dilution factors, but if all your dilution factors are the same, you can simplify it that way. So 1 over 5 to the power of 7 will get me 1 over 7, 8, 1, 2, 5. So my dilution factor is that. Now let's plug, right, that into our equation. 1 over 7, 8, 1, 2, 5 times my initial concentration, which we remember is 7. That's going to equal times 7, 8.96 times 10 to the 1, 2, 3, 4, 5 to the power. Super easy to do. You need 2 equations. How to figure out final dilution factor and how to figure out final concentration. Now that we've looked at scaling down, we can look at scaling back up. Let's say we've already counted all of our bacteria on a plate. How are we going to know how many bacteria are in that original colony? Well, we'll scale up, and that's what this section is about. So scaling up, when we count only a fraction of what was originally there, how do we account for that? Like I just said, we scale up, and there's an equation for this. And it is literally just a rearrangement of the equation for scaling down. Final concentration divided by final dilution factor equals our initial concentration. So we just rearranged that formula that we previously used. So you still only have to remember one. You just have to know how to manipulate formulas, which you should all know, to scale back up. So let's do some scaling up practice questions. I did a series of dilutions with an overall dilution factor of 1 in 20,000, and that plate grew a 1 milliliter sample after 1 day. I counted 27 CFUs on that Petri plate. How many CFUs would have been there in the original stock solution? So let's write that equation down. So I'm going to write the one for scaling down because that's the one I memorized. So final dilution factor times initial concentration equals final concentration. And I'm just going to rearrange that formula. So initial concentration equals final concentration divided by final dilution factor. Cool. Now we just plug and chug. I believe it gives us everything we wanted. Here's our final dilution factor. And here is our final concentration of bacteria units. So it will be 27. Oop, that is a 5. That didn't erase. 27 divided by 1 over 20,000. When we plug that into a calculator, we will get a final concentration, right? Final or initial concentration was going to be 540,000 colony forming units. So now that we know how to scale up and scale down, how do we pick the right number of plates to count? For this, we use the rule of thumb that your plate should count between 30 and 300 colonies. Anything more than that, you're going to get a lawn. Anything lower than that, you're not going to have enough to count. So here below, you can see an example, literally a lawn of bacteria, too many to count, they're overlapping. This is a good number, not many overlapping. I can see individual colonies. There's not enough there for me to be able to do anything with. And then finally, let's do one example of putting it all together and making sure poor old Frank is okay. You sample 2 milliliters of Frank's blood and dilute it as shown. How is Frank doing? So first, we want to count or pick the plate between 30 and 300. Now you can pick either one of them, but I'm going to do the easier one because I like easy numbers, and I'm going to do 178. So I have 178 as my final concentration. So final concentration equals 178. Then I'm going to find my final dilution factor. I'm going to see how many times do I do this. 1, 2, 3, and I have an initial dilution of 1 over 2, so 4. So I'm going to do 1, right? 1 initial dilution factor times dilution factor 1 times dilution factor 2 times dilution factor 3. Cool. So 1 over 5 times 1 over 5 times 1 over 5 times 0.5 would equal my final dilution factor equals 0.004 or 1 over 250. And then we can just plug it into that concentration or the equation, which would be initial concentration equals final dilution factor divided by final concentration. So, I'm sorry, I flipped that. Final concentration divided by factor, which would look, like IC equals 178 over 0.004. So it would be, my answer would be 4,000. Frank is not looking too hot here, right? He's not doing awesome. Does this make sense on how we put it all together now knowing what these things are? If you have any questions, please don't hesitate to ask.